Okay, so we're going to talk a little bit about um, Fourier series, Fourier analysis in general, and especially from the basis or from the viewpoint of linear algebra and orthogonality and eigenvectors and diagonalization. So it's going to be pretty cool. And I'll show you basically, we'll start with just where we're going. So we're pretty used to just computing um, just A. You can, if A is a matrix, you just have a vector here. I'm going to call it F. So A times the vector F is going to be some other vector. I'm just going to call it F prime for now, right? And so you can just do this computation and normal linear algebra, right? You can just multiply A times F and then you'll just get F prime, right? But we also want to do this in sort of the most smooth way that we can, in sort of an optimized way. And one of the best ways to do that is to diagonalize this matrix using the eigenvectors, right? So if we have A is the matrix in discussion, and then we have S, so S is a matrix whose columns are the eigenvectors, right? And then times this diagonal matrix, this is an uppercase lambda, and then S inverse. So if A's eigenvectors span the space that A is in, so let's say, A is a three-dimensional 3 by 3 matrix, then if you have three linearly independent eigenvectors, then you can do this diagonalization, right? So we can substitute this in for A up here. So then we have S lambda and then S inverse times F is going to be equal to F prime to that vector, right? So this right here is just another way of doing this multiplication. Um, and so where we're really going in this video is we want to discuss this in terms of Fourier analysis. Because let's think about this. So what if instead of a normal finite dimensional space, what if you were talking about function space? So let's say f is a function and a is your differentiation operator, and f prime is the derivative of f, right? So now let's do d of dt of f of t, right? And again, this is a vector, and this is, analogous to a matrix, right? It's a linear operator. This is going to be equal to f prime of t, right? And so now, this is sort of where we're going. And what happens is in Fourier analysis, if you want to compute this derivative, first you take the Fourier transform, and then the derivative is super easy, right? It's just some function times f for the derivative. Differentiation, once you're in the Fourier domain, is super easy to do, and then you just do the inverse transform to get it back, right? So you've got your function, you do your Fourier transform or your Fourier series expansion. Then this lambda, this diagonalized matrix, is the same thing as just multiplying everything in the Fourier domain to do the derivative, and then taking the inverse Fourier transform, and that's what gives you f prime. So this is where we're going here. So this S inverse times f, this is the same thing as taking the Fourier series expansion, right? So S inverse of f right here is the Fourier expansion, right? So this is where we're going in the end. And so that's our final goal, and we'll get there and we'll explain kind of the cool parts about it and why the Fourier expansion is as special as it is. Um, so with that in mind, there's a couple things we want to show first. Um, so that was number one. I kind of wanted to explain where we're going. And then number two is discuss change of basis. And this is a relatively quick part. Change of basis. Okay, so whoops, didn't mean to draw that. So in a change of basis, if you have some some matrix over here. Let's say it has V1, that goes, the columns are your vectors, right? Then you have V2, this is a vector, and then V3 is a vector, just like this, right? And now you have some, B2, B3, B1, so this is a vector here. And now you have A1, A2, A3. So let's say you have a vector. So you have A1, A2, and A3, right? So you have these numbers. But you want to write it in terms of this other basis over here. So what you want is you want these scaling factors. So you want B1, B2, and B3 to write this same vector, but in terms of this basis, right? So if we call this V, and this B, and this A, to compute B, all you need to do is take V inverse times A, right? And so now you have B. And this is fine. You can totally do this. You can do it, assuming it's not singular. You can compute this, and you can just do it with Gauss-Jordan elimination or however you want, but you can get B. And the key that we're showing here is whatever, if you have a vector written in terms of some basis, and you want it written in another basis, you need to multiply what you have by the inverse of that basis matrix to get your new coefficients, right? So, and again, we'll show that a little bit later. All right, so wanted to get through that little part. So number 3, we want to talk about transforms, and I think we already did that mostly, but let's go through it here anyway. So transforms. So we did, so when we did S, and then we had this, the eigenvalue matrix, and then S inverse times F is going to give us F prime, right? And these are vectors, right? This is just normal. So we're using F, but I don't mean it function right now. It's just, any vector in whatever space we're in. So if we want, we can multiply by S inverse on both sides, right? So if we multiply by S inverse on both sides, now we have F prime is equal to S inverse over here, and then F prime there, right? And so this right here was the equivalent of taking the derivative in the Fourier domain, right, in the frequency domain. So let's just kind of forget about that for a second. This right here was doing the Fourier expansion, right? So S negative 1 times F, right? So this right here is Fourier expansion. Now this is great, and this goes well with the change of basis that we talked about, because S is what we want to write. This is the matrix of the eigenvectors, right? This is S, right? So these are the eigenvectors of whatever our transform was, which originally I think we wrote it as A. So these are the eigenvectors of A, and we're wanting to write whatever our function was, which was F, right? We want to write F in terms of the eigenvectors. But remember, in the change of basis, we multiply F by S inverse, and boom, that's exactly what we're doing right here. So this Fourier expansion is actually just the change of basis matrix, or however you want to say it, to get whatever our vector is written in terms of S, in terms of these basis vectors, right? So they go well together, and this is lending evidence to that we're doing exactly what we want to do. All right, so now section 4 is we want to talk about computing S inverse F. So remember, if we have S, then we have lambda, and then we have S inverse, times F. Let's say we want to compute this, right? Well, if we have S and we want to get S inverse, we can just do, so we want to compute S inverse F. And, that's fine. We can do that because if we have S, if we have the eigenvectors, right? Let's call them, I know I've been using V, but let's use E, E1, E2. So these are all the eigenvectors, 3, right? Then all we have to do is, assuming that they're linearly independent, we can take the inverse or do the Gauss-Jordan, and then we can calculate S inverse, and we can just multiply by F. So this right here, that's analogous to computing the Fourier transform or expansion, right? And in this finite dimensional case, it's pretty easy. You just invert the matrix, it's no problem. So now we've pretty much done it. We've talked about transforms and things like that, but now let's move on to the case of actual Fourier, and it's going to be infinite dimensions now. So this is the key. All right, so let's do this. So if S is, I'm just going to do cosines um, because I don't. We can do sines and cosines. Either way is fine. But so let's just do cosine of 1t, right? And then cosine of 2t, cosine of 3t. And so this goes on forever this way, right? And these are functions going this way, right? So if we have S is this, right? So this is what we want to write our, these are eigenvectors of differentiation, right? So these are eigenfunctions or eigenvectors of the differentiation operator. Because when you take the derivative of this, it just, that one pops in front, but it stays the same, or maybe it's negative, I can't remember, I can never remember. But in any case, these are the eigenfunctions, right? So that's why S is this, because these are the eigenfunctions of our operator A, which was D, ooh, that's not a good D, of D dx, right? So these are the eigenvectors of that. Okay, and then, whatever I can't even remember how to take the derivative in the Fourier domain. I think it's just multiply everything by S. So that's this, right? And then so now what we want to do is, so we're here and we're computing, right? So what we want to do is we want to do S and then do our change of basis. So we want a new vector here such that F, right? Because we want a linear combination of each of these items in S to add together to give us F, right? That's the whole idea of a Fourier expansion, right? Is you find this vector of B's such that, you have some number multiplied by this plus some number multiplied by this plus some number multiplied by this gives you your overall F, right? So this is what we want. And so what we also want is we want to take S inverse right here times S times B, because that will just give us B right here. So we want S inverse F, which again is the exact same thing that we've been doing, right? Yeah. So now we're here, and let's go on to step 6. So if S, so 6 is sort of the final part. So if S is this cosine 1t, cosine of 2t, cosine of 3t, and so on, right? But we want S inverse because we want to multiply that because we want S, then that S inverse times our original function here. So what we want is just this part to do the Fourier expansion. So what that means is we need to calculate S inverse. And remember in the finite dimensional case, we had S, so to calculate S inverse, all we had to do was use Gauss-Jordan elimination or something, or compute the inverse. But now we have infinite dimensions, right? So how do we calculate the inverse of S if we have infinite dimensions and these are functions? And to be honest with you, I don't know, but I do know one thing, that's honestly essential at this point is in an orthogonal matrix, the inverse is the transpose, and that's our key. So, and that's why Fourier transforms are so special, is because each of the basis vectors are orthogonal, right? So S inverse is just the transpose of this, because if your matrix is orthogonal, then its inverse is just the transpose. So S inverse is the same thing as S transpose, which is the same thing as cosine 1t, cosine of 2t, cosine 3t. And I know I should have signs in here too, but I just want to give you the flavor, right? And this goes down forever. So this is our inverse, right? And now we're on the home stretch because we have f and we have s here, or we have our s inverse now. So all we have to do is multiply this times f. So I'm just going to go ahead and write f like this, f right here, and now I can write f. I like to write it sideways, right? So I like to write f of t, and then like this. And then as with normal matrix vector multiplication, what is each row in the result? Well, it's just the inner product, right? So the inner product of this and cosine of 1t, and the inner product of that and cosine 2t. So like this. So the inner product of cosine 1t and f of t, inner product. Now inner product of cosine of 2t, f of t. And then cosine of 3t, f of t. And then so on. So what is this? This is your Fourier expansion. And that is exactly what S inverse times F is. So we may have gotten a little bit lost in there, but there's a couple key things that make the Fourier series or Fourier expansion so special. And the first is that these cosines are the eigenfunctions of differentiation and integration, right? So that's why these basis vectors are so important, is because they make up this S for diagonalizing your differentiation operator, right? So these are the eigenvectors of differentiation and integration, and they're necessary to diagonalize the differentiation and integration operators. Okay, so that's one thing. So when we talked about that, we also said, like in the finite dimensional case, we also wanted our eigenvectors to be linearly independent so that they span the space. So that's another thing about the cosine and sines and the Fourier, is that the word in infinite dimensions is complete, right? If you take infinite sums of these, they will make this f, right? So they're complete, they're eigenfunctions of integration and differentiation. And there's one final piece that actually didn't matter that much in the finite dimension case, but did matter in the infinite dimensional case, which is what we're working in now in the Fourier, is that your eigenvectors or eigenfunctions, they didn't need to be orthogonal in the finite dimensional case, because you can take the inverse of it. But to take the inverse in the infinite dimensional case, I don't know how to do it. Someone might. But since we were orthogonal, we could take its inverse because the inverse is just the transpose, right? So that's the key. And that's the beauty. It basically, Fourier analysis has all of the three beautiful things in linear algebra. It is a basis of eigenfunctions. It's a complete basis or linearly independent. Also, it's orthogonal, which allows you to do this computation. And if one of those things didn't hold, all of this kind of falls apart. I mean, that's not totally true because you can still do a few things. But basically, the orthogonality is necessary to do the inverse, so that way you can compute. And I guess maybe we should just drive this home. So these are the coefficients on these functions to make f, right? So this inner product here times cosine of 1t plus this inner product here times cosine of 2t plus this inner product is that. So what we can call it, this is sort of like f of s, right? So then like f of 1 would be this times cosine of 1t, right, plus f of 2 cosine of 2t plus and on is going to be equal to f of t, right? Um, and so yeah, that's all we really wanted to get to, and why Fourier analysis is so amazing is because it has all three of those properties. So thanks a lot.